But what this compound interest formula didn't account for was the realities of how accounts work. If I have, for example, a savings account or something like that, I'm not just going to put a certain amount of money, the principal, and then just leave it there. The reality is I'll be spending money or I'll be adding more money into it, and the compound interest formula doesn't really allow for those kind of calculations. What we want to do is we want to combine our knowledge of series and incorporate that into a financial sense. And a very common thing and a very common thing to work with is money in a super fund. Right? Super is money that is saved from when you're working and then you can access when you're older or retiring. And each year you're depositing a certain amount. And so it keeps growing and growing and growing. You don't just have the same amount that's in there and leave it there. So let's look at this kind of scenario. A sum of $1,500 is invested at the beginning of each year in superannuation fund. If interest is calculated at 6% per annum, how much will be available at the end of 25 years? Okay. So there's a lot of things going on. The first thing to notice is that I'm not just putting $1,500 and leaving it there. I'm actually putting $1,500 at the beginning of each year. And I want to know the total worth at the end of that duration of time. Now, this can be quite tricky because we've worked with compound interest formula questions before, but I want to think about how can I account for the fact that I'm adding $1,500 each year. What I want to do is I actually want to break this down. Let's just think about the first amount that I have. For the first amount, I put in $1,500. So that first year, I put in $1,500. How long is that amount actually in the account for? Well, if I am wanting to know how much will be available at the end of 25 years, that first amount that I put in year one, I will have left in that account for 25 years. So just on that initial $1,500, I can think about that as using the compound interest formula. This is my principal, $1,500. My rate is 6%, or I'll write it as 0.06, all to the power, what? Well, n is the number of periods, how long I leave the money in the account for. And if this is the first time I've deposited that money in year one, I will have left it in there for actually 25 years, right? 25 years. Because I've put it in year one, and I want to know how much it will be worth at 25 years. And remember, this is just the first amount that I'm adding in. And I'm just going to rewrite this as 1,500 times 1.06, or 25. Okay. What about the second amount? Because the second amount I would have put in the second year, sorry. Because remember, I'm putting in $1,500 each year. Now remember, the principal is still the same. I'm still putting in $1,500 each year. And the interest rate stays the same. That's still 0.06. But how long will it be in my account for? Because remember, I'm putting it in the second year here. Well, it would be in there for 1 year less than the first amount, right? So that'll just be to the power of 24. And I can keep extending this idea, okay? If the first amount has been in there for 25 years, the second amount has been in there for 24 years, what about the 24th amount? Well, all I'm doing is I'm counting all the way down until that last year, that 25th year, the 25th amount. I know this will be in here for 1 year. What about that second last amount that I'm putting in? Well, that would have been in there for 2 years. Should be 24. Should be 2 years. And that last amount, well, that's the last year I put money in there. It's only actually in there for a single year. So, what have I got now? Well, remember, the original question was to work out how much will be available at the end of the 25 years. And so I know that an initial amount that I'm putting in will be worth this much. That second amount that I'm putting in will be worth this much. And so on and so forth until that last year, this is how much that $1,500 will grow to. So the question I'm actually trying to answer is the sum of all of these values. Right? The sum of all of these values. The total amount would equal to 1,500 times 1.06 to the power 25. I'm just grouping those two there. And then the second one, 1,500 times 1.06 to the power of 24, and then all the way until that last one there, 1500 times 1.06 all to the power 1. Whew. There's actually quite a few terms in there. So when I look at this, I could try to do this manually, put it on my calculator, and that would get the right answer. But I want to think a bit smarter than that. I want to think, is there a different way that I can answer this question? And there actually is. Instead, what I can do is, remember, I want to come back to this idea of a series. And I can see that there is a lot of these 1.06 terms. What I want to do first is, I just want to see what's in common here. I can see there's a lot of 1.06s, and I can see there's a lot of 1500s. Now the 1500s, I can actually just factor that out, okay? Because that's remaining constant throughout all of the terms. There's only a single 1500 there. I'm just going to factor that 1500 value out. And I'll get left with 1.06 to the power 25 plus 1.06 to the power 24, and so on and so forth. Okay. This is starting to look a lot more like a series now, right? If I just focus on this component over here, don't have another pen. Let's just look at this part over here. I can start to see a series emerging. Think about what would be your values that you need in order to determine this sum, right? Because we've learned the sum of a series. I know I can find the sum of series using the a times Rn minus 1 over R minus 1 formula. I really need my A, R, and N values. And I know how many terms there are. It's quite easy. There's actually just 25 of them, because I'm going from the powers of 25 all the way back down to 1. So there's 25 terms. Now A and R are a little bit trickier. If I just took the series from this order, from left to right here, you would think that your, I guess, first term would be 1.06 to the power 25. And it's right, you can find that really easily. That's T2 divided by T1, which is 1.06 to the power 24, all over 1.06 to the power 25, and we can simplify that using index laws. That's 1 over 1.06. Now, that's not incorrect, but there's actually a much easier way to see this problem. What I can do is, I can actually just rearrange this. And all I'm going to do is, instead of writing it from left to right, I'm going to write it from right to left. Okay. What I mean by that is I'm going to rewrite this as 1.06 to the power 1 plus 1.06 to the power 2, and so on and so forth, all the way until 1.06 to the power 25. And now the reason why I can do this really just comes back to basic addition, right? 3 plus 2, well, that's equal to 5. But that's also equal to 2 plus 3. So it doesn't matter actually which order I write this sum in, it's still going to be the same value. So now I can rewrite my A and R values a lot simpler. What's the first value in my series? That's just 1.06. And if I wanted to find the common ratio, the term I have to multiply this to get to the next term, well, that's actually quite easy, right? That's just 1.06. And again, if you're struggling to find that, you can use the T2 over T1 definition, but I think that's quite intuitive there. So now what I want to do is just sum up this series, right? I can find that using my partial sum of a geometric series formula. I just need to substitute in my values. So S of 25, that would be equal to A, 1.06 times R to the n, 1.06 to the power 25 minus 1, all over the rate, 1.06 minus 1. I think you get 58 from that one, from memory. 1.06 times 58, oh, you get some nice decimals. 58.156, all the way there. Let's just keep that value in our calculator. And let's just multiply that out times 1500. So, wow, you get $87,234.57. Awesome. So, that's the total amount that is That's the total value of the account at the end of that 25 years. Remember, I'm adding in that $1,500 amount each year. Just out of curiosity, how much interest is that? Well, if I put in $1,500 each year for 25 years, that's just 1,500 times 25. That's actually only $37,000, $37,500. It's not a small amount, but you can see how much your account has actually grown over time. If you take the difference between those two values, minus 37,500, right, you've gotten about $50,000 almost in just interest. So that's really the power of interest, and the way that we can calculate that growth is using this partial sum of geometric series.